What's up, guys? Sup. I'm back. I'm gonna continue on this Turing Complete a little bit. I want to see if I can get past this next level. These levels get like way harder. I like the way the music fades in. You guys can't hear it yet, but I can because my speakers are loud. If I bring the volume up, you can, but I'm gonna pull it back down because it gets louder and louder. So the delay line allows us to save a value for one tick, so it's basically a latch. So save, enable, save value, output. When the first input is green, update the save value. The second input is the value. Always output what is currently saved. This is the diagram. Okay, so this is the save line. This is the delay line. So this is a switch. We'll need a switch for sure. I don't think this is gonna be it, but let's try it. We failed. No, we didn't. It is almost that simple. I knew there was gonna be a gotcha. So when the save is off, okay. We need another switch. And then we need a clear switch. So, not on. Nope. If there is a value here, let's see, what do we do? This is not right, but this is not right. I know it's not right. Hmm. Let's look at what's happening. Switch is on. Oh, because both of these are off. So in the case where both of them are off, we need to create a latch. That's what we need to do. So I think we need another switch here. This is not right at all. I know it's not. I should know how to do this. Let's see. Let's look up and switch. I'm pretty sure we gotta have a double latch. That's what we need. Yeah, okay, I remember how to do this. Oops. So we do in and, we do two in ands. This is the switch. And this is the value. So when we get a value, it triggers this one, but the in and latch should never have both inputs off. Oh, we got that one wrong. We're almost there. Oh, this is for reset switch. This would give us a reset. This is not. Surely it's not that easy. Let's see. We need this is what I was trying to do the first time. So, but okay, instead of using switch, we're gonna use So this will negate itself. So one of these will always be off. So dang. Not it. We're close though. What if we just do this? I don't think this is it either. Yeah. Let's try this. Okay, so this is our data line. And the control goes to both. But this one acts as a latch. And then these two feed back into each other. And this one becomes our data line. There we go, that's it. So let's go through the logic again. So here the save line is on, and it tells us to save the value, which triggers this to be not and, which sends the value through. And this is a negation, so it makes itself true because both of these are on. Again, these are both still on, so we have it on. We have the save line on, which tells it to save. Triggers an off here. Both of these are off, which then sends a negation value, which says that it's off. We could also follow the logic this way, where this is not and here, which triggers this to be off. This is an off value. It's a little bit tricky in and logic. The same is true again. Both are off, which triggers both in ands to be on. This one, well, this one's off and this one's on at the same time. So these would like self-correct essentially. The value here essentially does nothing, because both of these still negate, which triggers this to be off. It's blocking. Same here. Again, we've already been through this state where they're both on. So the save line controls both of these. This value is still sending through, but it's because this save line is considered off by this second negation. I wonder if we can achieve the same thing with a single NOT gate here. But again, because the save line's off, nothing happens. Let's see if we can use a NOT gate here. If we use a NOT gate, what happens? So NOT gate fails because it doesn't have that negation coming through in this save off state. So we do need that in-and circuit. So it does require double in-and with a loop back on both of these, and that's how we get all of these values. Okay. It's pretty close. I did have to do a little homework, but that's okay. Let me pull up Kick because I can't see chat. Looks like Kick's working today. Hello, Johnny V. You changed your name. Delete these spammers. This level has two types of inputs. 2 byte inputs and 2 byte outputs. Your goal is to copy from one of the inputs to one of the outputs. The first bit input determines which input you should copy from. The second bit input determines which output you should copy to. Okay. So, we have a switch, 8-bit switch. So we need a NOT gate. We'll need a double NOT gate. And a double switch. So both of these will have to be cross-connected. And these will be directly connected. We might not get this right the first time, but it's okay. Oops. So one of these will allow it through, and then one of these will pick which output it goes to. So we gotta have the NOT gate here. There we go. From input 1, oh, this is input 1. Okay, so it wants these swapped as well. Okay. It looks like it's working. Yep. So you just use double negation. So in one case, if the switch is off, then the first switch is on, and if the switch is on, then the first switch is off and the second switch is on. And then we do the same thing for the outputs, and we just cross map it. So then no matter what, we only allow one input and one output. Oops. Another way we could do this, just to make this look a little bit cleaner. Oh, interesting. Oh, you know what? It's because there we go. There, now you can see we bridge the inputs and outputs, so it doesn't matter. Yeah, so saving bytes. Create a circuit that can save or load a byte. When the first input bit is green, load the memory and send it to the output. When the second input is save the input byte. Output has an enable pin. Enable it only on load. So this is load. One bit of memory. Okay, so oh, we created a multiplexer. I did not realize that. Switch. We're going to use the byte splitter, and then we'll use the bit saver. So we'll have 1, 2, 3, 4, 5, 6, 7, 8. I don't know if this is how it wants me to do it, but this is how we're gonna do it. We'll try it at least. Four, 8. So these act like a big memory chip. Individual bits being saved. So this toggles a bit save on each one of these at the same time. So this acts as a latch. And then this should output. Let's start here. 128, 64, 32. I want this to be a lot cleaner. 32. 64, 8, 4, 2, and 1. And we can connect all of these. I have no clue if this is gonna work. I hope it does, because I spent a lot of time making this thing. Let's see. Action save. It should save its values. Load and save. Start state. Output should be. Output enable should be on. Isn't it? Oh, are these backwards? Is this the output enable and this is the value? Well, that's silly. Save. There we go. Okay, so the value was on the left, the enable was on the right. So we still have the 244 saved here. And then 33 is just doing nothing because the actions do nothing. So this gives us 8 bits of memory, essentially. Do nothing, 244, 244. Just run through all of them. It looks like we passed. I think that's what we had to do. Yep, level complete. So we can move on. So we have a 1-bit decoder. or a counter, or the sign negator. So the sign negator one like really stumped my head yesterday, but I don't want to redo it yet. Let's do the 1-bit decoder. Create a component that can switch a signal between two pins. Input. Like, I know this isn't what it wants, but like I think I don't know how to give it what it wants. Is that really all it wanted? Oh my goodness. Okay, 3-bit decoder, little box. Let's do a little box and see what this is. Can you fit 4 bytes of memory in this limited space? In this level, you have to build a circuit that can save or load from 4 different bytes of memory. You're given 1 bit that determines if you are to load, another bit to determine if you are to save. And it comes with a corresponding value. Additionally, you have 2 address bits. Within 2 bits, there are 4 combinations. Okay, I already know how to do this. Tip, join wires in the middle and use right angles, or this will be a mess. Spacebar rotates components. I did not know that we could do that. Okay, so this is our value. A or B, 0 or 1. 8-bit of memory. I wish I knew what these little dots were for. Oh, I do. Save, load. So this is the load. This is the save. This is an 8-bit register. Let's see, we need to have... Won't let me zoom in anymore. Let's see. So this output, expected states. 128 tests we gotta pass. Address, so I think these 2 are the addresses. A or B and 0 or 1. So toggles between 2 values. Select 1 or 2, input 1 or 2. I don't know how to decode this. If this is, oh, wait. Let me reread the instructions. How do we, let's go back and reload. Can you fit 4 bytes of memory in this limited space? Oh, I see. It's gonna load different values. Okay. Input 1, input 2. So we are gonna need multiplexer. I think we're gonna need 2 multiplexers. And then this state, so the load state, let's see. I don't think I can load a window over this window. So it won't let me not full screen this. Dang. Let's see, what am I trying to do? If we have a switch, toggles a bit on. We're gonna need like exclusive ores, I think. We don't need a switch, we need so we'll need so this is load. This is save. So there's different ways to do this. There are more than one ways to do this. So we're missing a piece here though, so we need to have a NOT gate. That's not right. So when it's off, we're gonna choose the first one. No, that's not right either. Save only needs to be on when we have this on, so we need to have an AND gate. That's the load gate. Oh, I got these backwards. Shit. This is so confusing. So, let's remove these muxes right now. I don't know if we even need those muxes yet. So when we have, geez, oh, this is tricky. When we have save and 1, save and not 1, save and 2, save and not 2, we bring these back. Then these will act as our savers. Let's change the color. Oh, those are the load switches. Oh, these are also our selectors, so we need to run the switches here. I have no clue if this is gonna work right. And then I think we still need to have these muxes. Which tell us which ones to load. So like, load A or B. Load B or C. And then this is A, this is B, C and D. This is horrible. Do we have them backwards? Expected states. Fuck, this hurts my head. I'm gonna look. I'm gonna take the hint here. Output has an enable pin. Enable it only on load. Can we just delete all of this? So the input goes in. Oh, we can use a 1-bit decoder. I don't know why I wasn't using that. And then memory. pretty sure this is not right, but kind of don't like this color either. We're gonna need AND gates, so I know that much. I know we're also gonna need as much space as possible, so there's our load bit. Jesus, my son scared the crap out of me. I just realized the music might be louder than my voice. So, so this would be the save lines. And then I think we still need to use the multiplexer to toggle between values. So we take the output here, the output here, the output here, and the output here, and then we use the decoder to control the load lines. Jesus, I just realized my mic's been off this whole time. For fuck's sake, man. Damn, I was explaining all this shit too. I was saying there's probably a better way to do this, but this is pretty straightforward. So like A and 0 have to be on here. In this case, it's A and 1. Very cool. So we've got a binary decoder. So off is the first one and on is the second one. And then we use our AND logic to determine if it's A and 0, A and 1, or B and 0 and B and 1. And then from there we have all of these mapped into a save line. These are all our save switches and all of our load switches, and those are mapped to our memory, our register. So we either save it or load it. So in address 0, we want to load. The expected output is coming out. We want to save 42 into B0, which is here. We can see B and 0 are on, which enables this. Our save switch is on, which enables this to go through here to trigger this, and then we save the value in. This loads the value. Same thing. Our load switches all of these on, but only one of these has a binary value coming through. So we're using this switch and this AND logic together to save 134 into A1. And so this creates an addressable memory. Using 2 bits, we can have a full byte of memory addressing. Save 54 into B1, so it looks like all of our states working here. Let's run through. There's 128 tests. Let's see if we pass them all. In our advanced civilization, forcing save 233 and load, expected output 195. Interesting, so it is loading and saving simultaneously. That's super cool. In our advanced civilization, forcing prisoners to do extremely menial tasks is slavery and is technically illegal. That is why instead we had our intern create the 256-byte version of your component. So now we've got 256 bytes of RAM. That's huge. So we're almost to the point to where we can run a program. Let's see about a counter. Counting is so fundamental, even insects do it. From counting, species can evolve to comparing to arithmetic, and before you know it, you have apes building computers. Make a device that counts increments 1 per tick. Build a counter will increase by 1 each tick. Additionally, there should be an option for overriding the counter with a given value. There are 2 inputs, a bit and a byte. The bit should... Why'd I go offline? Looks like my live dropped for a minute. That might have been my connection to my live. The bit input should toggle between counting and overriding the value of the byte. So we need an on switch. With a delay line. This is not right at all, actually. Actually, suck at this. actually really suck at this. Like not the whole thing, but like creating counters. This is a hard one for me. Add one to the counter or override it. Adds 2 inputs. I have no clue if this will work. I'm thinking that the delay line when it's off, it should switch itself on. And then when it's on, it should switch itself off. And then, we want to have a byte that adds 1. Wait. We want to convert this bit like this should pass the first test. So 1. Okay, and then we want to 3 bits and outputs the sum. I think we could do this actually. I think we can say input 1. We don't need 3 bits though, but like bit of memory. We don't need to register that way, I don't think. What am I trying to do here? I don't know what the frick I'm trying to do here. Eight-bit switch. Okay, I do know that we want this. What am I trying to do? My brain is like shit in the bed here, y'all. If anybody that's watching knows the answer, I appreciate if you just give me the answer. Eight-bit maker. Toggles between 2 values. I think we're gonna need something like that actually. And we'll need a 8-bit maker, 8-bit splitter. Oh, I see. We're gonna need the 8-bit adder here. Okay, I think this is right. We want to add this value. We're going to carry in 1. Yes, we're going to carry in 1. This will be the result. And then we'll feed the result back into itself. No? Do we actually have to decode and re-encode? Like, that would be really stupid, but... I feel like we do have to do this step, and I don't like it, but... The output of the component leads back to its own input. I know. We're gonna have to use the memory. In each step, we want to save and override itself, and then go back in here. I don't know if this is gonna work. Add 1. Add 1. Oh, fuck my brain. We need it to like save in 1 step. So adding 1. So add 1. Okay, I see here. When we add 1, we need to save. And then when we're not saving, we need to load. So we add 1. And we saved 1. We add 1. We should have 1 here. Do we save and load at the same time? Add 1. Do we not load it? How about we load every time? It's delayed. I feel like we do need a piece of memory though, like... one bit of memory. But this register is memory. Just always save and always load. So we're adding 1. What am I missing? Like it's saving the 1, but it's not outputting the 1. Like it saves 1 here, but the output's still 0. It's like there's a delay in the memory. And it won't let me use a byte splitter. I'm so confused. Do I have to run a decoder and build a second latch? Like, I don't need a full adder. I mean, this is the adder that we need. We need the input. And then we can't feed the result back into itself. It won't let me. Like, that would make the most sense. Can we use the mux? Nope. I mean, we will need this multiplexer to choose between our memory, but what I don't get is why it won't let me use an 8-bit register. Also, I don't even know why I have an adder here. One. I'm still not sure why it won't let me just like pop this in here and then pop this back around here. Really, we should be using this carry in. And then save and load should be on all the time. Like, this should work. We add 1, but see, now we're not getting the 1 output here. Like, this should be 1, but we're not loading the 1 because we're still loading the 0. But we're not using the switch, so I don't understand. Like, now it's loading the 1, but it's not giving us the 2. We need another piece of memory here to tell us when to load. This should always be on save. This is like driving me crazy, man. There's a delay. There's a delay in the memory. There's always a delay in the memory. We'll add a tick. See, but now this line's off, and yeah, I know, it's always going to negate itself. That's why we need the delay line. The delay line works too. And thus we need a 1 bit of memory. I don't understand, man. Yeah, I'm gonna pull the solution up because there's something I'm not understanding. And of course, this froze the fucking game. Are you kidding me? We're not playing shapes 2. Why did it? Game is frozen. Computer's like going slow for some reason. So I did have it on memory load. It's using a binary adder this way.
You still need to always load.
I mean, that's almost what I did.
The end until it asks me to.
Okay. I mean, that's basically what I fucking did. We'll try this again. Okay, what we're gonna do is we're gonna have this on line. We're gonna have an add line. We're gonna have our 8-bit of memory. The memory will always be on. It'll feed back into itself. And then we'll have a mux with a bit delay. It allows us to choose between the values of this one and this one, and then we'll just output this. And then the value will feed back into itself. So you add one, and then it doesn't work. It freezes here too.
Always save the noise. But you see it, the level will stop, but we already see it can count to 4. So override. I can tick until
Again, man, it like the game literally freezes when I try to pull up the menu.
we're asked to be
Oops. Let's try it again. Like, I think this is right. I'm not understanding why this isn't working though, because we should be able to have an 8-bit register of memory. And an adder. I see we need to output the added value. So now we have 1. Now we have 2. Okay. It's trying to output this value. Oh, I see. Okay, so then we move this here. Oh, wait. This is our counter. Wait. So the added value, what am I doing? The multiplexer goes into the memory. Memory goes into the output. And the added value comes back into the multiplexer. So, because we need 1 tick. Here we have the 2, then when we switch the 33, we're overriding the memory with 33. There we go. That's how you do it. It's a little bit of a recursive problem, but it's fine. Finally, I want to relook at this again though. So we're constantly adding 1. That goes into our multiplexer. If we're not overriding the memory, we're going to store it. Then we are always saving and loading, so it's always 1 tick behind. So that's where I messed up before, is I had a delay line. The memory already has a delay line, so we need to feed the output of the add back into itself. So the add will always create a delay of 1 tick because of the way the memory operates. So it's loading 1 while it's saving another. Then the multiplexer allows us to overwrite the memory at any point, because we can overwrite the output by switching to a direct write input. So this allows us to control ticks. With 3 bits of inputs, there are 8 combinations. Building 8-bit multiplexer. Make a circuit that selects one output for each of the 8 combinations. No more or less than 1 bit should be green at a time. Yep, 8-bit multiplexer. Okay, well we will tackle this one next time. I actually enjoy doing these. We can use 3 bits because we can count from 0 to 7, which gives us 8. These are fun, but I'll catch you guys next time. I gotta go take care of real life. Thanks for tuning in. I'll catch you guys on the flip.